We'll examine section 1.2 in the lay textbook on row reduction and echelon forms. This will be the first of 2 days. On the second day, we will practice. So this could be thought of as a bit of a flipped classroom. This is the bread and butter computation and algorithm that is used in a linear algebra classroom. Excuse me. Before we get started, let's just try this multiple choice warm-up. The number of solutions of a system of linear equations cannot be which of the following. And it turns out that the answer to this is that you cannot have exactly 2 solutions. So C should have been selected. Now the question might seem theoretical, but it's important to treat these types of questions seriously in a linear algebra class, because our goal is to eventually describe the behavior of all linear systems, not to just do a computation in one linear system, right? It's about what's going on kind of overall for linear systems in general. The fact that each equation in the system is linear is a crucial aspect of this. So we are only going to look at linear equations. If you had nonlinear equations, then there really is no answer that would have worked for this multiple choice question. And it's important in this class to state definitions in coherent sentences. So I would encourage you to, every time you look at a definition, to really digest the meaning of the definition. What is it really saying? You can't really just ignore definitions in this class that might have worked in a calculus class where there was really only one key definition you may have dealt with, but in this class you will need to use definitions very carefully in order to compute and prove and so on. So the main goal is to learn this method that is used to solve a system of linear equations. We will look at linear equations not most of the time in its original form, but in this recording device called a matrix, and more specifically we'll look at this augmented matrix. The algorithm we're learning is called Gaussian elimination, or Gauss-Jordan elimination, or row reduction. We will first look at reviewing the elementary row operations, and then talk about the kind of shape we want is sort of looking like a triangle, and we'll talk about why that's useful, and then we'll learn a methodical procedure to get there. I would encourage you to do your work by hand. Do your work by hand as much as possible, but then you can verify the work you're doing using this thing provided by Dr. Grice. It is a row reducer that is written in Flash. And as the elementary row operations are reviewed here, please, I would encourage you to think at home about why these processes are allowable. Okay, so the 3 elementary row operations are right up here. So first you can replace a row by the sum of itself and a multiple of another row, key being that the row that you're replacing, you can only have one copy of that row. And we'll see examples of that in a moment. You can swap 2 rows or interchange 2 rows. And then third, you can multiply all the entries in a row by a non-zero constant. Okay, those are the 3 row operations. You will master these very quickly. And let us then now talk about why a triangular shaped system would be good. So if you had a system of linear equations, or linear system that looked like this, you could solve this without really much work at all. Now this would be the corresponding augmented matrix, right? Take a look, there's a 0x1, so that's why there's a 0 here, a 5x2, that's why there's a 5 there, and so on. The numbers over here that are to the right, you can separate the numbers in this column using a vertical bar here or not, doesn't really matter. But the reason this triangular shape that you see here, or this kind of triangular shape you see here is nice, is you can use back substitution. So take a look at this last equation, the bottom equation, 6x3 equals 18. That's easy to solve, right? You divide both sides by 6, and you get that x sub 3 has to equal 3. And now that you know that x sub 3 is equal to 3, take a look at the second to last equation, right? You just plug in the 3 right there, and then 5 times this one variable minus the number 3 is equal to 2. We know that x sub 2 has to equal 1. That's forced by equation 2. And now that we know the numerical value of x sub 2 and the numerical value of x sub 3, we can use the first equation. And we can find out that the value of x sub 1 actually also happens to be 1, right? But like, the point is, if all 3 equations use all 3 variables, then there'd be a bit more work involved. This triangular shape is really nice. In other words, having these zeros is really nice right here. Okay, so the shape we're looking for can be triangular, but that might be asking for too much. So more generally, we want a shape that looks like this, and this is what's called echelon form. So the matrix that we're looking for should have this general shape to it. This is sort of a generic, kind of a cartoon sample of what one looks like. So in any row, the first entry that is not a 0 is denoted using this solid square. And then these asterisks, these stars, are denoting entries in the matrix that can be any number. So it could be 0, could be non-zero, any real numbers allowed. And then, of course, we're using a 0 to represent, to say that that spot, that entry in the matrix has to be a 0, right? So you have like 0, 0, 0. Oh, there's a first number that's a non-zero. So this spot right here, it's a cartoon, but this is a symbol trying to suggest that the number here could be 8, or it could be -7, or could be 12, could be pi, could be 7/8. Any of those are fine. This entry then could be any number, could be a 2, could be a 0, doesn't matter, right? But the first non-zero entry is represented by this square. Okay, so the type of thing we're looking for is called echelon form, and the key things are this, is that the echelon form, first off, the leading entries, that is where these first non-zero entries are called the leading entries, these have to stair step, right? They create, like if you just looked at these alone, they have to, the next one is below and to the right, can't be directly underneath. And then the point, the other key thing here is that wherever you have a leading entry, all of the entries that are below in the matrix must be a 0. So there's this box here, the solid box, meaning that this is a leading entry, a non-zero number. All the numbers below have to be 0. Here's another leading entry, so there's the first non-zero entry in this row, and all numbers below have to be a 0. Same thing here, all numbers below this have to be a 0. And then finally, only zeros, a row that is completely 0, those have to appear at the bottom. Okay. So take a look at these 4 matrices. Which of these 4 are in echelon form and which are not? Go ahead and pause, and then take a look for a moment. Okay, welcome back. So the 4x5 matrix, that is this one here with 4 rows and 5 columns, this is not in echelon form because the third row here is a row of all zeros. That should be at the bottom. So in fact, we would have something in echelon form if all we did was we interchanged the third and fourth row here. Right? So yes, oh, there it is. Sorry, forgot. So the row of zeros should be at the bottom, or the 0 row should be at the bottom. Finally, this 3x5 matrix is not in echelon form, and that's because we don't have the stair step type thing, right? So the fact that we have the leading entry of the second row and the leading of the entry of the third row right here, this is not considered a stair step. We should not have the first non-zero entry being in the same column here and here. This is actually easily fixed using one of the row operations. Here are 3 matrices that are all in echelon form. So let's take a look. Leading entries are here, here, and let's see, the leading entries right there. So take a look, stair step between where the 5 is, the 7 is, and the 9 is. The leading entry in this next matrix, we've got a 2, a leading entry right here of -8, those stair step, and then your rows of 0 are at the bottom. You have leading entry, you have a leading entry of -73, and then your row of zeros at the bottom. And again, you have the stair step, right? You don't have the situation of a leading entry and then a leading entry directly underneath. That can't occur. So we're going to revisit pivots the way the author defines pivots. There's like a very strict definition to that a little later, but for now I would like you to think about these 3 definitions that are interrelated. First off, a pivot position of a matrix that is in echelon form. So if your matrix is in echelon form, let's clear this up. You have a matrix in echelon form. A pivot position is the location in the matrix of the leading entry. A pivot column is a column that contains a pivot position, and a pivot is the entry, that is the number that is in the pivot position. So we'll clarify using this matrix as an example. Here's a matrix that is in echelon form. So here's one pivot position, and what I mean is the location, right? So I mean not the 5, but this upper left corner, the location where the 5 is. Think of this as the difference between you and your house, right? Your house is an address, right? That's a location. So don't think of the 5, that would be like you, right? The 5 is occupying that location, but the location, this position, that's position, this spot, and then this spot, and this spot, those are the 3 pivot positions. And so since this location, don't even look at the number, right? The point is this non-zero, there's a non-zero here, there's a non-zero there. Those leading non-zeros, those are the pivot positions. And the pivot column, here's the first one highlighted in red, but another pivot column, well, because 7, well, where the 7 was located, was a pivot position. This column, 470, that second column is a pivot column. And finally, there was a pivot position right here. Again, I'm not trying to say the number 9, I'm saying this location. I'm using the mouse to point to that spot, right? So then this 4th column is a pivot column. Finally, a pivot is the number. So 5, that's the distinction with pivot position. 5 is a pivot, 7 is a pivot, 9 is a pivot. Those are the numbers. Okay, let's take a look at these other matrices. We have this location are pivot positions. This column and this column are pivot columns, and the number 2 and the number -8 are pivots. In this matrix here, also in echelon form, here's a pivot position. This is the location of a pivot position. Again, I'm not saying the number -73. The number -73 and the number 2, those are pivots. And then pivot column, right here, the first column and the second column. Okay, the algorithm that we're looking at is a little tedious at first, but it takes a little getting used to, and then it's going to be fine. What you do is you begin with the first column that you have that's not completely zeros, right? Now you look amongst the columns. If you have a column that's all 0, that's fine. Move on to the next column over, but find the leftmost column that has a non-zero somewhere in the column. This is a pivot column. This is a pivot column. I promise this will be a pivot column, and the pivot position is going to be will need to be at the top. So what you do is within this column you might have some numbers that are 0, some numbers that are not 0, some entries that are 0, some entries are non-zero. Select a non-zero entry in the pivot column to be the pivot, and what you'll do is move this where this number that you have, if it's not at the top, just interchange rows so that you have this at the top. Then do the row reduction operations to create zeros in all the positions below the pivot position. And then once you've done that, you're good in that column. Then you can cover that row, freeze the row as is, and then do the same thing to all the rows that are below, which form what's called the submatrix. You just basically repeat. So let's take a look at a number of examples. So here's a matrix. Right now you have a leading entry here, there, and there. Those are the first non-zero entries in each of the rows. So that's not a stair step. We don't have something in echelon form yet, so we'll go ahead and need to do some of the elementary row operations. So because this is the first non-zero column, this will be a pivot column. And now what we do is note that we can interchange and swap, but I don't mind leaving the 1 here, but now we need to make sure that there's no 1 here. We need a 0 here. And the way we're going to do that is we're going to replace row 2. So the new row 2 is going to be the old row 2 minus row 1. So when we do that, we should end up with this. So in other words, I'll point as I do it. 1 minus 1 is 0, 2 minus 1 is 1, -4 minus -3 is -1, -5 minus -2 is -3, and -2 minus 0 is -2. The key thing about using this elementary row operation is if you're going to replace row 2, you got to have 1 copy of row 2, and then you can add or subtract any number of copies of a different row. You cannot have a coefficient in front of this row 2. Now, having the 0 is good, right? We're well on our way. We need a 0 here. We shouldn't have a 2 here. I'd like to have a 0. So how are we going to do that? Well, we could replace row 3 with, again, we'll start with row 3, and then how about we add -2 copies of row 1, right? So the new row 3 is old row 3 plus -2 copies of row 1. Again, the number in front of this right here has to be a 1. This is one of the things about technically being an elementary row operation. We going to have a 1 right there. So let's reveal the matrix that we get, right? So the first row, the second row of this matrix, they're the same. This is just a copy paste. The only difference is in the bottom row, and let's just see, right? What happened was we took the 2 plus negative 2 times 1 is 0, and then 0 plus negative 2 times 1 is negative 2, and then negative 2 times negative 3 plus a negative 4 is 2, and so on and so forth. And now take a look. We've got zeros there. So this column is good. Now that we've got zeros underneath, we freeze this first row. So we're not going to touch that row anymore. Now let's take a look at what remains, right? In the next two, the only 2 rows that we're allowed to touch, because we've frozen the first row. We look now in this first column, ignoring the first row, right? We've got these zeros, so right here we've got a non-zero, well, either here or here, and so either of those can be our pivot. If we like, we can leave the 1, but if you want the negative 2 to be up there, then you can swap the 2 rows. We'll just leave the 1 right here. And now we need to do a row operation, right? So let's keep this one here, but we shouldn't have a negative 2 here. So negative 2 plus 2 times this number would be 0, and we'll replace there, right? So what we'll do is we'll now make row 3, the new row 3 should be the old row 3 plus 2 times row 2, right? And you'll get a thing like that, right? So just to make sure, 2 times, for example, negative 3 plus 6 is going to equal this 0 that appears right there. And take a look. Once you've done that, we have a matrix that is in echelon form. Here's leading entry, here's leading entry. We've got that stair-step look along with that bottom row of zeros, right? So we're done. To summarize our work, we started with this matrix and ended up with this matrix. These 2 matrices are called row equivalent. It's just we started with a matrix that was not in echelon form and ended with a matrix that is in echelon form. And we can do this algorithm to any matrix, including, we'll often do this to coefficient matrices, and we'll often do this to augmented matrices. Now, augmented matrices, if you'll recall, have that extra column from a system of linear equations in that it's all the data. It has the constants that are on the right side. And in fact, if we viewed this matrix that we started with as an augmented matrix for a system of linear equations, then this would have been the system of linear equations. Take a look, compare the numbers there and there. And after we've done the row operations, we have this. And what would this look like as a system of linear equations? Pause the video, write down the system yourself. Okay, I hope you've now unpaused the video, and on the next slide I have, this is what the system would look like. I mean, there's only 2 equations if I go back 1 slide, because here you have 0x1 plus 0x2 plus 0x3 plus 0x4 is equal to the constant 0. That's not really any information at all. So you really only have 2 interesting equations. And the point is, this is that almost triangular-like thing, right? This echelon is the next best thing we have. And the point is that this new system of linear equations has the same set of solutions as the old original system did. And how can we describe the solution set? Well, let's do the following. Let's x3 and x4, let's say that they can be any real numbers. And just to emphasize that they can be any real numbers, let's introduce t to represent x3 and u to represent x4. Then take a look at this bottom equation. If you solve for x2, you get this, and let's even use our new variables for emphasis that this x3 is becoming a t, and x4 becomes a u. So we have x2 is equal to t plus 3u minus 2. And then take a look at the first equation here. If you solve for x1, you'll get that. And if we go ahead and copy the minus sign, but replace the x2 that we see here with this t plus 3u minus 2, we should throw that in parentheses for sure. 3 times replace the x3 with a t and replace the x4 with this u, and we have that. Distribute the minus, collect like terms. I didn't bother showing you all that work, but you will end up with 2t minus u plus 2. So With that, here is the solution set. So this is written in one of the standard notations for sets. The point was that after the colon, you can choose any number you want for t, any real number you want. You can choose any real number you want for u, and once you've done that, well, the third coordinate is what you chose for t, and the fourth coordinate is what you chose for u, but the first coordinate is right there, and the second coordinate, t plus 3u minus 2, comes from right there. So this is a solution set, right? There's many possible solutions. There's not just one solution. Anytime you pick a number for t and pick a number for u, you'll have a solution. So for example, you can pick different numbers if you want, but if you picked t to be 10 and you picked u to be -8, then you'd get, let's see, 2t minus u. I mean, you should check, right? But 2 times 10 minus -8 plus 2 is going to equal 30, right? So you get this 30, x1 being 30, x2 being -16, x3 being 10, and x4 being -8. That ends up being a solution to this system of linear equations, to these two equations, and in turn, because the row operations are valid things to do, the original system of linear equations with the 3 equations, this is also a solution to that original system of linear equations as well. So let's try another example and find the solutions to this system of linear equations. There's 3 equations here, 1, 2, 3. Because there's only 3 variables, just up to z, we didn't use the subscripts, we just called the variables x, y, and z. So if we take this information, record the entire system of linear equations into an augmented matrix, again, you can draw this vertical bar to separate the constants, -6, 1, and 11, but you don't have to, whether the bar is there or not. No, don't treat this any different. It's just for visual emphasis. There are many ways to do this, and so let's, just to try another elementary row operation, let's decide to scale the scale the second row by a factor of 3. So all I did was copy paste the matrix, and just every number that was in the second row I just multiplied by 3. That's all that happened. Now what I'd like to do is take a look. There's a 3 here, there's a 3 there. I'd like to do this number minus that number. So the second row minus the first row stored in the second row. Again, the key is that the coefficient in front of the row that is being replaced has to be a 1. So you can have a number in front of another row that's not a 1. Like here we have a -1 in front. That's fine. But in front of R2, since R2 is getting replaced, we got to have a 1 there. So let's do that, right? This minus that stored here, this minus that is stored there, this minus that is stored here, this minus that is stored there, and we should get this matrix right there. So the only difference is in the second row. Good. So we have this leading entry with zeros underneath. That's great. Now we can freeze the first row. We don't need to deal with that anymore, but take a look here. We've got a 1, so we've got a leading entry, we've got a leading entry. That's no good. They can't be right on top of each other. So how about we do row 3 minus row 2 stored in row 3? I bet that's what happened. Yeah, that's what, again, there's many ways to do it, but that's what I chose to do when preparing the slides. So the new row 3 is the old row 3 minus the old row 2. So 1 minus 1 is 0, 5 minus 4 is 1, 11 minus 9 is 2. Now take a look. That matrix is in echelon form because you've got a leading entry there, there, and there. Again, as far as dealing with is the matrix in echelon form or not, you should not let the vertical bar enter the discussion for that. So you should actually ignore, erase the vertical bar when answering, is this in echelon form? Yeah, leading entry, leading entry, leading entry. If you have non-zero entries to the right of a leading entry, it doesn't matter. You can have 0 entries, non-zero entries to the right. Either way is fine. Okay, now what happens in this example is that each column is a pivot column. Right here we've got a pivot, it's a pivot column. There's a pivot, pivot column, so here's a pivot, and there's a pivot column. And so there's going to be no free variables. Unlike our last example where we had x3 and x4 to emphasize that they were free variables, we had a t and a u to say that you can pick any real numbers you want. In this example, there are no choices. There's nothing that is free. Everything's going to be fixed, in fact. Right? So we started with this matrix. We did our row operations. We got this matrix. So this matrix and that matrix are called row equivalent. And let's take a look, right? Nothing is free. There's no choices at this point, because we see that 0x plus 0y plus 1z equals 2. In other words, z equals 2. And now that z is equal to 2 from the last row, which is the last equation, then the second to last row, we have 0x plus 1y plus 4z is equal to 9. And since we already know that z has to equal 2, we get that y is equal to 1. And now that we know the value of z and y, we can step back one more time, use the next row above, which happens to be the first row, and this right here, we end up seeing that x has to equal 0. So there's only one solution. The single solution is this right here, 0, 1, 2. Okay, here's the thing. Based on this echelon form, once you get the matrix in that form, you can answer these two fundamental questions. Does a solution exist? In other words, is the linear system consistent? And if so, if there is a solution, is the solution unique? Is there more than one solution? So let's take a look at this. Let's say that this was an augmented matrix, right? Interpret this not as a coefficient matrix, but as an augmented matrix. How many solutions are there here? I want you to think about that. Well, let's take a look at the bottom row. What is the bottom row saying? If this is an augmented matrix, meaning you can visualize a vertical bar here, these are the 2, 5, and the 7 are the constants that are on the right side of the equal signs, then what's the bottom row? 0x1 plus 0x2 plus 0x3 equals 7. Now think about that. The left side, 0x1 plus 0x2 plus 0x3, simplifies to a 0. In other words, whoops, excuse me, oh dear. You have, drop the mouse there. You have this equation, 0 is equal to 7, right? There's going to be no solution there. That's inconsistent. And this is something, I mean, this is really just kind of exploring by example, but this is what happens in general. So how do you know that you have an inconsistent system of linear equations? Well, take your original augmented matrix, do your row reductions until you get to a point where you have echelon form, you have that stair-step thing, and if you have a row that is all zeros except the number over here you have a leading entry in the rightmost column, the column reserved for constants, then you have an inconsistent system. Okay, so let's take a look at some more examples. So how about this? We don't have that situation. There's a 3 here, right? But had this been a 0, we'd have the same problem as earlier. We'd have inconsistent. But here, we don't have that issue. So there's consistency. In fact, here's the equations written out. We see, for instance, that x sub 5 is forced to equal the number 4, right? But then there's going to be more than one solution here, because if x sub 5 is fixed to be the number 4, that's fine, but then x sub 4 can be any real number, x sub 3 can be any real number, and then x sub 2 will just depend on x sub 3 and x sub 4. Right? So x sub 2 you could say is like a function of x3 and x4, but x3 and x4 are free to be whatever you want. And because x3 and x4 are any real numbers that you choose or that anybody else chooses, you can automatically already see that there's an infinite number of solutions. Right? So now that x5 is fixed to be 4, x4 and x3 are any real numbers that anybody could choose. x2 is now forced, and then now that those variables are all known, x1 is forced. Okay. So we have this terminology that I'd like to introduce, and don't want to be too formal about it, but the forced variables are these basic variables, in this example x1, x2, and x5, and then the unforced, like the variables that are free to be any real numbers that anybody would want to choose, those are the free variables. And take a look, that information is very well encoded in the matrix as well. Right, so this is the column for the first variable x1, here's a column for x2, here's a column for x3, column for x4, column for x5, and the column for the constants. And every column that is a pivot column, right here, first column, second column, fifth column, those correspond to the basic variables, and then the non-pivot columns, in this example, that is the third and the fourth columns, those are the free variables. It works out very nicely. Okay, so this, just to finish this system is consistent and has infinitely many solutions. Let's look at another example here. So what about if we view this as an augmented matrix? Here's the corresponding linear system. There's this real boring row of all zeros, but that just says zeros equals 0. No problem there. But then take a look at the remaining 3 equations, which are the interesting ones. Take a look. There's no free variables, right? There's every column is other than the constant, the column that reserved for constants, every column for a variable is a pivot column. Okay, so we get, if we go through x sub 3 is forced, you can solve here and see that x sub 3 has to be -1. And now that we know that x sub 3 is forced to be the number -1, the next equation above forces the value of x sub 2. And now that we know that x sub 2 is forced to be positive 8, there's no choice allowed, then the equation above, we see that x1 is also forced in value. And so in this example, all 3 variables are basic variables. There's no free variables at all. There were no, every column that corresponded to a variable, so every column other than the column on the right, these were all pivot columns, and so there were no free variables. And if there's no free variables, if there's no choices to make, you can see that there's only going to be one solution. Okay, this is a consistent system because there's a solution, but this time there's only one solution. So here are 3 of those sort of cartoon-like pictures. Just recall that the solid box means a non-zero number, and the stars mean any real number. Could be a 0, could be a non-zero. But take a look at these 3, which are in echelon form, and pause the video to answer for yourself which of these 3 has a solution, and if there is a solution, is it unique? Okay, so let's take a look at this first one here. Don't let this throw you. If the 0 had been here and the solid box had been here, we would say no solution, right? We'd say inconsistent. But this is just saying that, what is this? The first variable, second, third, fourth, fifth. The 5th variable, x sub 5, right? This box, let's just pretend that there's a 5. Let's pretend there's an 8 there. Then this is like 8 times x sub 5 equals 0. That's okay. It's just we would divide both sides by 8 and then learn that x sub 5 is the number 0. So that's fine. No problem here. There is a solution. Okay. This is a consistent system. Solution exists, in other words. And it looks like we've got here a non-pivot column that corresponds to the 3rd variable. The 3rd variable is free. X sub 3 is free, so there's going to be an infinite number of solutions. And I should, yeah, okay. And then in addition, x sub 1 is free. Okay, the next matrix down, let's see. Well, you've got this bottom row that has 0, 0, and the leading entry, you have a non-zero entry right there. That's what that solid box means. And so you really, this equation, if you really think about it, is 0 equals whatever, 38 or something, right? So no solution, inconsistent. Over here, we don't have a row that looks like this of all zeros and then finally the last number is a non-zero. So this is consistent. And then notice that among the columns corresponding to variables, there's no, let's say it this way. All of the columns corresponding to variables, meaning every column except the last column, is a pivot column, so there's no free variables, meaning there's only one solution, right? Because there's no choices that can be made at all. Okay. So we talked about echelon form, and there's a special kind of echelon form that's called reduced echelon form. So not only do you have this echelon form that we've been dealing with, and we've seen some examples of how to get to, but in reduced echelon form, it's like a special kind, there's additional things that have to occur. So in our original echelon form, there were these solid boxes here, meaning any non-zero number. Well, in the reduced echelon form, any non-zero number is not okay. Now it's a specific non-zero number, it's the number 1. Okay, so that's, yeah, there we go. And that's actually easy to achieve. The next part is a little harder to achieve. So maybe I'm skipping around a little bit, but how's that easy to achieve? Well, let's say this number is an 8. How do you get a 1 here instead of an 8? You just multiply every entry in this row by 1/8, right? Just the reciprocal of 8. What if this number here was a -5? We'll just multiply every entry in this second row by a -1/5. What if this number is I don't know, 3/5? Then you just multiply every number in this first row by 5/3. Just a reciprocal, and then you'll get that 1. So that's not too bad. The other thing is, in the more relaxed thing of echelon form we were dealing with, as long as you had this leading entry stair step, then anything could happen to the right of a leading entry. You could have zeros or non-zeros. And for leading entry, or where a pivot is above there, you could have any numbers as you want. That is a little different in the reduced echelon form, in that where these leading entries are, which are now of course 1s, above you have to have zeros. So there's a 0 here, 0 there, and a 0 there. That is the difference, where here there's a star that says you could have whatever you want, and these 2 stars, yeah, they have to be zeros. So one of the key things to note is that when you take a matrix and you do your row operations, there are many matrices that you can get that are your final answer. If you need it in echelon form, there's many different looking matrices that are all in echelon form. But this reduced echelon form thing is going to be completely unique. And if we go to the book's definition of pivot positions, this is why I wanted to kind of do our thing earlier in the presentation, but the pivot positions are where the 1s end up ultimately being in the reduced echelon form. It's just hard to talk about the reduced echelon form before you get there. And this is a bit of a repeat, but the columns that contain the pivot positions are the pivot columns. So the thing is, this matrix is not in echelon form, right? Because of that 0 here, and well, other issues, like these are all trying to be leading entries. But once you have a matrix that is in echelon form, you can already know the positions of the leading entries. You can know where the pivot positions are from any echelon form matrix, not just the reduced echelon form matrix. Again, I want to emphasize that there are many echelon forms. So if you have a question where you have a matrix and you just need to get into echelon form, don't freak out if your answer is going to be different from a classmate's if you're comparing your row echelon form, REF, to somebody else's row echelon form, REF. But if the instructions are to get a reduced echelon form or a row reduced echelon form, or REF, then there's only one, right? So then everybody should obtain the same answer. So what do? Well, first off, you give the matrix and you first get it into echelon form, as we have done, and then once you have a matrix in echelon form, what you do is you now basically start from the lower right. And so starting at the rightmost pivot position, you work upwards and and then move on to the left and create zeros above each pivot. Okay, so after your scaling, right? So yeah, you do all these scalings to make sure that you have 1s for leading entries instead of any other non-zero number. And we'll see an example here on the next slide. So on the next slide, we'll start with a matrix that's in echelon form, but not yet in reduced echelon form, and then we will get the matrix to ultimately be in reduced echelon form. So let's start with this linear system, right? It would already correspond to a matrix that's in echelon form, but this is not in reduced echelon form. Now, the fact that the leading entries are 1 is good, but because these are the leading entries, or rather there's a leading entry here, so the numbers above need to all be 0, but there's a 2 here, problem. There's a leading entry, and the numbers above need to all be 0, but we have a 1 and a -1, problem, right? So what we can do is, let's see what happened from here to here. Let's skip some steps just to save some space on the slides, but you can see, for instance, let's take let's get a 0 here. So what you need to do is take row 2 and replace it with row 2 minus row 3, right? again, because we've got to make sure that the coefficient in front of row 2 is a 1. So this minus that goes, well, we should do it for all the entries, but it's just the fact that we have zeros here makes it already nice. So 0 minus 0 is stored here, 0, and then 1 minus 0 is stored here, 1. 1 minus 1 is 0 stored here, and then 4 minus 2 is 2 that's stored here. Same sort of thing. Let's think about how, instead of having so that's how we achieve this 0 that's right there, but then how do we achieve, instead of having a -1 here, how do we have a 0 in this spot? So we do need to update this row, right? So it should be row 1 plus some multiple of row 3. It looks like it's just row 1 plus row 3 stored in row 1. So 1 plus 0 is 1, 2 plus 0 is 2, -1 plus 1 is 0, and then 1 plus 2 is 3. Aha. So yeah, we did 2 row operations in one. It's just kind of skipping some of the work. And then let's take a look. So the fact that we got zeros over here, good. We need to have not a 2 here, but rather a 0. So we're going to update the row 1, meaning we should think of row 1 plus some multiple of a different row. So how about row 1 plus -2 times row 2? Yeah, so 1 plus, let's not say plus because we're doing -2 times the second row. So how about 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 0 minus 2 times 0 is 0. 3 minus 2 times 2 is -1. And there we have it. And the great thing about the reduced echelon form, at least as far as a matrix, augmented matrix goes, is that we can read things off right away, right? So this says from the bottom, going back substitution, x sub 3 equals 2, x sub 2 is equal to 2, and then 1, yeah, so x sub 1 is equal to -1, right? Because this is really saying 1 times x sub 1 plus 0 times x sub 2 plus 0 times x sub 3 is equal to -1. I do want to draw your attention to this. The slide has a second purpose, which was to just explain that if you had something in echelon form, right, as we have here, you can do your back substitution, and there's a little bit more work involved here in finding the solution, whereas when you have something in reduced echelon form, you can just read off the solution kind of right away.